microphone.
Carry on with the second talk of this afternoon session. So it's a pleasure to introduce the next speaker, who is Aurelia Chenu, a colleague at the University of Luxembourg.
Thank you very much for the introduction, and thank you very much for the organizer for putting together this nice workshop and for the invitation. The work is on dynamics of noisy, and I added non-Hermitian quantum system. And this is a work that's been done in collaboration with Adolfo Del Campo and others at UNILO. So I very quickly want to introduce the University of Luxembourg that just celebrated its 20 years anniversary last year. So it's quite young, the youngest in Europe. It has this, one of the campus, the physics department is like next to this city center that's very nice and pretty, and they're constructing, renovating an old minery site, which is in Belval in here, which is of a different style. And this is the group of people that is working with me. And so, as I mentioned, I will be working, presenting about work that's been done with Adolfo Del Campo and led by Pablo Martinez Ascona and Aritra Kundu, who is also in the audience here. So what we do very much in the group is study like open quantum systems as being seen like from either you can think of these as, for example, natural light harvesting systems, or more controllable platforms like artificial systems. And the theory that we try to work out with these open quantum systems is for the quantum simulation, we have like some applications to quantum control, and as Aritra mentioned, some application to noisy devices. But the program as a whole aims to use noise as a resource. So the systems are intrinsically coupled to some environment. And instead of trying to develop, to model this environment, the program that we started is basically adding by hand stochasticity to some H0, like deterministic system, and see what we can do with this. So I'll try to show like very briefly two applications on these quantum simulations and spend a bit more time in here. I'm just standing here because the pointer is not working, which is a bit annoying. But so as a very quick warm-up, and that will be very fast in this community, for open quantum system, where you can think of a system coupled with a bath, then you know that the full evolution should be unitary. But if you're interested, or if you have access to only a small part of the system, then you can obtain a Lindblad master equations. And there's different kind of unraveling. And as has been seen, like in this audience many times, if we, for example, we take a time-dependent Hamiltonian to which we add some noise, so that would be my Wiener process, Gaussian white noise, then at the level of these Hamiltonian, the dynamics is closed. I can write a stochastic dynamics, and once I do the average of like all the realization of the noise, then we find Lindblad master equations. So one of the first things that we looked at is to see, can we do something like beyond Lindblad? And the first idea that was following the idea from Feynman on quantum simulation is to say, okay, well, maybe we can engineer some Hamiltonian, let the system evolve for us, and do measurements that bring us like physics that we would not be able to observe otherwise. So let me do like this, that would be faster. So the first thing we did was looking at what happens if this Lindblad operator becomes like a many-body operator. For example, it acts on like 2 or like k spins, for example. And well, in that case, the dissipator does have like a Lindblad form, but it's a bit different or generalized in the sense that we have here repetition of like the indices, in the sense that we built up correlation between the I1 IK and I'1 I', k. So what does this lead? Well, this leads to the dynamics that have a very, very fast decoherence. And for example, in this case, the decoherence time scales polynomially with the K range of the Lindblatt. So to show like how that would change, for example, in if you apply this kind of dissipator in some particular platform, for example, the Bose-Hubert, where you would add noise on the on-site interaction in here. Well, in the dissipator, you start to have many-body interaction in the sense that having noise on the same on the sites. So it's very important that it's the same noise that is applied on all the sites, because then the different sites become correlated through this long-range dissipator. Similarly, if we do something here on the Ising chain, where we would add noise on the hopping, then we start to have a many-body dissipator with longer range. So if you look at the dynamics, for example, well, you see that for like, even as you increase the system size from n equal 3 to n equal 5, we see some survival of quantum revival as we add the noise. So again, here through the noise, the particle starts to be correlated because they see the same oscillation. So one of the things that we did applying this model through noise is, can we engineer some dynamics that allow for faster control? And this was in the framework of this shortcut to adiabaticity. So very quickly, let me mention, so the shortcut to adiabaticity, the goal is to turn a process that is slow into something that is arbitrarily fast. You can determine and decide in which time scale you want to do it. Of course, if you go too fast, then you're going to create some excitations. So the trick is to add in the Hamiltonian that you started with some terms that will cancel this excitation, so that at the end of the trajectory, you have the same state as you had, as if you would have gone adiabatically. So this has been developed first for closed system, and the framework is really is the following. So consider that you're driving the system with some reference Hamiltonian, and for these you can write the adiabatic approximation. The question is, can we find a Hamiltonian h of t such that the adiabatic state is the solution of this generator? And this was developed by Demir, Parak, and Rice, and independently by Berry later on, as yes, we can find these terms. So the way to do it is to start with the reference Hamiltonian and add some correction, H1, which is known as the counter-diabatic, so that we have parallel transport and we don't have any transition between the eigenstates. So there's been lots of work on these in the closed system, and I'll only flash here some experimental demonstration that were done first like for single particles, then for like condensates, and with Adolfo, and we worked with we implemented this, we worked in collaboration with experimentalists to implement this in a strongly interacting Fermi gas, showing that we can control the expansion and the compression of the Fermi gas. So, but we were asking, okay, well, can we extend these techniques to the open setup and consider that we have some environment? And this question has been looked already by in the group of Vlatko-Vedral back in 2014, and it was quite mathematical in the sense that it was using this concept of adiabaticity in Liouville superspace. So we looked at this in a very specific system, simple harmonic oscillator, and at the same time that Paul Kovnikov and others were working on it. So around 2019 and 2020, apparently some people were interested in that. So the question is, can we control the harmonic oscillator, for example, or a general open dynamics? So in this paper here with Sahar Daripur and Adira Shakani, we have like we show how we can actually implement this dissipator. So what we do is we start with an open dynamics, any kind of open dynamics, and then consider that the unitary term can be described by this counter-diabatic Hamiltonian that was developed from the closed system, and then add a dissipator. And there would be like two ways that one could think of how to implement this dissipator. One would be through a Lindblad-like kind of master equation that takes a non-Markovian rate. And another way would be to add a non-Hermitian terms to take care of this dissipator. So without going into the detail, I want to show like an application of like how we could use these to engineer the dynamics of a harmonic oscillator. And that brings me back to this stochastic Hamiltonian where we add noise to the system. So the setup now is a harmonic oscillator where we allow for the frequency to be time dependent. And we now add on the position, we add some stochasticity. So you can think of it that you're like shaking the trap of your harmonic oscillator. As I showed very briefly before, if you do look at the density matrix on the ensemble average, then you find something that is Lindblad-like. Here we have a gamma t, the rates that we put in front of the noise, that is time dependent, and that's instrumental for the scheme that we have. So before, when people were doing this expansion and control of harmonic oscillator in the closed setup, there's no possibility to change the entropy. So if we look at a map of here as function, the inverse final temperature over the inverse initial temperature, and here the same for the frequencies, the range of systems that were at reach from the closed dynamics is on this line where we have no change of entropy. And of course, if we want to change the entropy, well, then you need to add some openness in the sense, you need to add some openness. So this is what we did with this scheme. And so that allows to reach any thermal state in a finite time. And now we can expand the states at reach to the full map. So where if this gamma of t is positive, we have a heating here, we have a production of entropy. And if we can engineer a negative gamma of t, then we'll get a negative entropy, so some cooling. Let me show you how it would look like in the lab. So imagine that you take a reference frequency as function of time, normalized on the final time of your shortcut. So let's say that you want to do some compression in this finite time. The black curves here shows like what is the frequency that you should implement in the lab to do it in a finite time while still staying as adiabatic. And if you look at the control frequency, well, squared, it's given by the reference one that you choose. And there's a correction factor. And for people who have worked with shortcuts, they might recognize this term as in the closed setup, it would be given by this adiabatic factor that's like highlighted here in red. But now, since we are like in the open setup, we allow for changes of entropy, and we have to allow for changes in temperature that are like accounted for here. So there's a correction. The formalism is the same, but we have an additional factor here that comes from the fact that it's open. So that is the first modification of the scheme. And the second modification is that now we have this dissipator that is controlled with a strength gamma of t that is also for the control. So in that case, we're doing cooling, and here we have like a negative gamma of t. That's the one that should be implemented to reach this cooling. And you see, we start from like some initial thermal state, we finish in a thermal squeeze state, but we always have like no correlation between X and P. So we did like further work with the PhD students, Léonce Dubé, to like actually be able to control how much correlation between X and P we can have at the end of the scheme. So this is one of the application of these noisy schemes to shortcuts to control. And now I want to spend a bit more time on this application of noisy devices. So yesterday we had a talk by Aritra Kundu that showed this stochastic operator variance that characterizes the spread of trajectory around the Lindblad master equation, the Lindblad solution, and how this can be related to an out-of-time order correlator, and that is used to diagnose chaos. So these we found looking at something else, that the density metric will, in that case, we were looking at any operator that was evolving under a noisy dynamics. So what I want to do here now is to see what happens if, in addition to be noisy, we also allow this noisy term to be non-Hermitian. So the setup now is quite similar, as you might recognize. I still have a deterministic H0 system to which I'm adding like noise through the L operator, but now everything is non-Hermitian. So I'm adding noise in terms of gain and loss on the system. Well, I can still write a master equation, but everything that was a commutator becomes anti-commutators now. That was because of this I. So, and importantly, the state is not normalized anymore because I can leak out of the subspace, effective subspace that is describing, that I'm taking into account. So if we want to look at the physical state that has a norm 1, we can normalize these just divided by the trace of the state. And here we have the normalized dynamics where we have a correction, and now the master equation becomes nonlinear in the states to account for this renormalization. So before I go further on showing like what is the dynamics generated by these Hamiltonian, I want to show like some results from Morse experiments on how to actually implement first a non-Hermitian Hamiltonian in the lab. So here is some beautiful results from cases that was like presented last week, where they can implement a non-Hermitian, effectively non-Hermitian Hamiltonian in the superconducting qubit. So what they do is that they have a 3-level system, G, E, and F, where there's some leakage from the E to the G level. They do continuous measurements on this level, and each time they have a click, they discard this trajectory. So that effectively looking at the E and F level, the Hamiltonian becomes non-Hermitian. If you look at the eigenvalues of these, well, then you see that according to this, the ratio of J squared on like gamma squared over 4, if this is positive, then you'll have like real eigenvalues. So you'll be in the PT regime. And here I'm showing from this paper, like what are the eigenvalues. So they're described by the Riemann sheet. We don't have this parameter, which is like some additional energy in here. So looking on this axis, then we have the imaginary part being 0 for like PT region. The eigenvalues are real. And then as the coupling increases between E and F, then we go in a regime where the eigenvalue become complex. So if you look at the dynamics, and they did like they were able to do measurements on how this looked like. So this is the probability of staying in the F state in here for the 2 phases here. There's a zoom. We have like in the broken phase, this is kind of like a steady dynamics versus in the unbroken phase, we have some oscillations that come in here. So I'll come back to this experiment later on, but now I want to come to our model where we did something very similar, take the same Hamiltonian, but then adding noise in addition on the decay here. Okay, so we have some decay, capital gamma here, and in addition, we add noise on it. And the question is, what is the dynamics that comes that is generated by this Hamiltonian. So we can write down the density matrix. This is the normalized one. Again, it's nonlinear the state. And then if we look at the nonlinear term that is given by the trace of the Liouvillean on a row, well, then we can identify three regimes in the sense that either the trace, this term is negative and then the trace decreases, or it's positive and increases. And at the transition, when the product here is 1/2, then we have a trace preserving dynamics. So what does this mean? Well, the first thing that we looked at is the purity, for example. So let's consider that you look at the evolution of the purity. And since this is a two-level system, we can compute everything like analytically, but like here is shown like the plane of the Bloch sphere with no noise. And the color scheme here shows whether we have a purification, we go into a purification or not. So this shows that with no noise, the state, if the system starts in one of the states, then it is purified. As the states, and here it gets more and more mixed. As we increase the noise, the small gamma in here, then we see that well, the states that are going to purify is like a smaller area. But importantly, after the transition here, then there's a switch into which states are going to purify. It means that whether you're, according to the level of the noise, a state that was here then purifies, but if you increase the noise, the state that will become pure change. And so we can really do some kind of, well, control the preparation of states on the basis of like how much noise we add in the system. So now let me show you a bit more like detail on this dynamics. And again, since it's a two-level system, we can solve analytically everything. So if you look at the Liouvillean, and here we can identify three phases. So this is a representation as function of like the decay over the coupling, and this is the strength of noise. So the results before in the PT broken and unbroken were at noise equals 0. So we were here with a transition from the broken to the unbroken phase. And as we increase the level of noise, what we see is that we have a new phase. So the color scheme here shows the Z direction for the stationary states. So this shows that in the PT broken phase, we go to the North Pole. Here we go to a mixed state. And here with this noise in this phase, the system stabilizes in the E state instead of the F state. So there's a switch of the steady state. Now, maybe you're wondering like how fast do we go to this steady state? And can we say anything around that? So let me show you like three typical cases according to where we are in this phase diagram. So in the PT broken phase, for example, where we'll be converging to the North Pole, here we have like the state vector that shows like how any of these states will go around here. And here I'm showing the eigenvalues of the Lindbladian. So to characterize the dynamics. So that's in the case of the PT broken, where we go to the North Pole. If now I look at the same thing, but for the different phase, so this is for like some value of the noise in the unbroken phase, then we see that all the states converge to the center and they become mixed. And finally, you might guess that if I look in this noise-induced phase, what's happening is that we converge everywhere to the South Pole. So now let me introduce, so this is showing the eigenvalues of my Lindbladian. Well, that's the Liouvillean. So let me introduce like what we call the dissipative gap, which is looking at the difference between the eigenvalues with the largest real with the largest real eigenvalues, and then the next, the one afterwards. So this controls the dynamics in the sense that the inverse of this gives the time scale of the convergence to the steady state. So let me illustrate this dissipative gap. And I think I'll show everything here. So this dissipative gap that we have as function of, so I went too fast. I'll stay here. So for the different phases, we can see how, how this dissipative gap increases in the noise-induced phase and is like smaller in here. And around this line, it becomes like smaller and smaller. So now what does it mean for the dynamics? Let me fix the noise as particular points. So let me take a transition here, fix gamma j at this value, and then see how the state evolves as a function of time. So here we plot the fidelity to the steady state. The steady state being able to change according to which phases we are. So if we are in the PT broken phase, we see that we develop like some oscillation in here until we converge. These are the results for the PT broken, and this is for the noise-induced phase in here. And what I want to highlight on this plot is this dashed white line. That is the inverse of the dissipative gap. And it gives like the time scale for convergence to the steady state, because then you can write your state as the steady state plus some other like state where that decay as e to the minus delta t. Okay, so here we see as we come like across this transition from the PT broken to the noise induced that this time scale is increasing, and then it goes again. And here, just for information, we have like the oscillation of the states. You can see here for the first oscillation, and this is given as the inverse of the maximal imaginary part of the Liouvillean. So now you might wonder, this is something I haven't like really mentioned is that, so I mentioned very briefly that we have a non-Hermitian dynamics. So we are not trace preserving, and the way that we do is that we renormalize dividing by the trace. And it's much easier, at least for us, to do like calculate the ensemble, the stochastic average of the density matrix, and then get the trace and do the normalization in this way. But if you think experimentally, the one that you might get is actually not the same average, in the sense that you might get the renormalized one as you do your counting, and then you do the average at the end. So these are numerical simulations that show the different way of doing the average. So here I'm showing the probability of being in the Z state and for the different phases. So where we see again like these oscillations in the unbroken phase, and here the noise induced that just decays, goes to the E state. And well, the good news is that from the simulation, it looks pretty, yeah, it's, if you inverse, yeah, sorry for the color scheme, I think it's inverse on these two. But we're confident that these two averages like give at least quite good agreements. So we're still working on trying to see like if we can get better, well, characterize better this kind of averaging. Okay, so now in the last few minutes, I just want to come back to these experiments and say, well, what this model would be good to. So this model was really a theoretical curiosity that we wanted to explore with Adolfo and saying, well, what happens if we put noise in the system? Can we engineer new kind of dynamics? And I've shown that, well, yes, we can do some things of like many-body dissipator. We can do something on control. And if we add like this non-hermeticity, we can also find new phases. But coming back at the experiments here, So where, again, this was the experiments done in the group of Keita Mosh, looking at these trajectories in the broken or unbroken phase. Here in this paper, there's a graph that shows that in the case that you have no like gap that is, so where we work here at delta equals 0, you would expect to be in the broken phase. So you would expect that you have no decay of your dynamics. So basically, this curve should be expected to be at 0 in the sense that there is no imaginative, there's no decay in your trajectory as being modeled by a perfect model, right? So, but it's obviously not the case from the experiments. So it happens that, so if we look at a single trajectory, for example, the black one being like the raw data and the blue is the fit. So we can extract what is the envelope of these decay rates around here. And doing so, what we find is that we can actually fit and infer what is the strength of the noise that comes in this experiment. So we're still working on this, but just to convince you that we think that we have quite a good model, here I want to show as function of the coupling as we go. We expect in this pretty broken to have like no decay, to have this at gamma equals 0, but the experimental dots in blue show definitely that there is some reminiscent decay because of the imperfection of this, the experiment. So in green here, so the black curve shows the model with no noise, small gamma equals 0. And in green, we show how we can capture these decay and find what is the noise that is intrinsic to the platform here. So this still work under progress, but before I close, I just want to extend these results to the general setting, because so I presented all the results in a stochastic qubit where we can work out everything analytically, but we can also like think of the general setup where you would have any deterministic system to which you couple any L operator with some noise. So in that case, we can also work out what is the purity. And I think that the important point is that if we look at the Liouvillean eigenvalues, then we can find the relevant states being the one that are the one renormalized. We call them like physical state in the sense that they have a trace 1. And then what is the dynamics going to? Well, the dynamics, the density matrix, once I average over the noise at long time, is going to this steady state that I showed before, plus something else. There's something else being like with a decay that's given by this dissipative gap. So that is like the difference between the two largest real eigenvalues, and with some the frequency oscillation being done here. So really, we go to this final state as fast as the dissipative gas is. It is working actually. Now it is working. So that brings me to my conclusions. So I did not like present or very briefly mention about like another work that was presented by Alitra yesterday on the stochastic operator variances and how this can help look at the deviation of around the main trajectory, the Lindblad master equation. I hope I've convinced you that if we add the noise, even if it's a classical noise, we can find new quantum dynamics. But there's also a trade-off between looking at the non-Hermitian setup. We find there's a trade-off between the dissipation that is in the system and the noise. And this kind of dynamics will allow for purification, but they also allow for control over the steady state in the sense that, for example, here we can switch and define as function of the noise to which states we want to go. Okay, with this I'm closing, and I want to thank you for your attention.
Hi, thanks for the talk. I wonder, is there a simple explanation to the mechanism when you stabilize the other state, when the noise becomes?
So yeah, we've been wondering on these. One of the explanation is that there might be a feedback coming back in. So if you look at the trajectories of like the gain and loss, we are like mainly in the loss, but as the noise becomes like stronger and stronger, you have a broader and broader distribution. There might be some of the trajectory that come in. We're not sure yet this is the reason, but that might be one of the possibility.
I see, because indeed, when your noise is strong, you have some positive decay rate instead of negative.
Yeah, so I think maybe having just a few number of these trajectories that are staying is enough for this, but I'm not 100% sure this is the reason. So we're still investigating this. So for the harmonic oscillator with noise, like the steady states? No, so we control the temperature. So we can define which temperature we want at the end. And that will depend on, yes, so on the map that I show, we can control what is the final temperature that we want. Here we would be able to, so you start with the thermostates with some initial temperature in this one, and if you fix the one that you want at the end, you would be anywhere here, right? So depending on like how you change your ratio of frequency, then you'll be able to implement it so that you build the temperature that you wish. So this is initial inverse temperature over like, so it would be T0 over TF. So you take your initial temperature, you start with a thermal state, and then you want to go to a final temperature that you fix as well. Once you have fixed this, you have to see like what can be like the frequency that you're allowed to go. So this is going from the initial to the final one. And with this scheme before, like if you have no energy, no entropy production, you would be able to access only one specific state. So imagine that you do a compression, but you have, since you're in the thermal state, you have to still satisfy like the Boltzmann ensemble, right? So if you don't allow for the like cross transition between the eigenstates, then there's just like a very few number of states that you can do if you don't change the entropy. And by allowing for changes in entropy for this gamma t, then you can redistribute the population of your eigenstates such that you reach the thermal state with arbitrary temperature.
So you're saying the long-term solution of this is not unique?
So we look at the finite time, right?
Finite, but it like, so it depends on like.
Well, at infinite.
Sometimes it heats up. Is that right?
Yes, and at the infinite time, you'll have like this decoherence in the x basis. So I wouldn't say it heats up; it just becomes.
There's no steady state, is that right? Or?
So it is not a steady state. We consider that we fix the time, but it is not the steady state.
I guess there's no steady state for this equation. Is that right? I mean.
Well, yeah, at steady state, you'll have like dephasing in the x basis, right? Yeah, so you might be hitting up like.
Well, at least the classical version, I would imagine it speeds up to infinite because there's no.
Well, I think it depends what you put in here. This is time dependent, so it's time dependent. So one of the way that we think how you could engineer this is to use like some feedback control, but it might not be obvious. I mean, trivial.
Any more questions?
Okay, thanks for the talk. I have a question. You said it's important to add the same noise at some stage. Why is it for? Because it's simple to treat, or is it there's any other reason?
So here, everywhere, it's the same noise. But the way that the way that I understand this for this like long range dissipator is that the sides become correlated through the noise. So one of the inspiration for this model was the light harvesting complexes. So in the community of quantum biology, there's like a two-level system, a chromophore that's coupled to a bath, and then there's another one coupled to a bath, and they're like normally the bath are not correlated. But then they say that there was like long quantum beats, like quantum coherence, and one of the hypotheses behind is that we needed like the harmonic oscillator, the bath, to be correlated. What happens is that if you have one of the bath that is like strongly coupled and the same that is correlated to the second one, indeed, then the two pigments that are originally not coupled become coupled through this mode. So this is exactly the same phenomenon that happens, that through seeing the same noise, sites that were originally uncoupled starts to be coupled through this bath.
Okay, thank you. And also, I have another question. Have you ever looked at the mean field approximation for example, Ising model that you consider?
No, we
No,
didn't.
No questions. I have one very quick one. Is there any analog of the sub-autocorrelation with non-Hermitian noise? You know, extension of Aritra's talk to non-Hermitian noise?
So you want the autark in the non-Hermitian regime? So no, I don't know. I would know like chaos for the non-Hermitian case from the spectral statistic. I'm not sure how this would look like for the autark. For the autark that we have in the sub-autark, it's through some dissipation one, but I don't think that accounts for the fact that it's non-Hermitian. So no, I'm not sure.